This is pH, pOH, hydroxide ion concentration, hydronium ion concentration calculations. But before we start any calculation, we have to look at a very, very important concept that will be used. This is self-ionization of water, or it's called auto-ionization of water. This is when two molecules of water collide. There can be a transfer of a hydrogen ion from one molecule to the other, as shown here. So you have hydrogen ion, proton from this water to the other water molecule. And then when this gives off the hydrogen, it becomes hydroxide ion. And then when this water accepts, it becomes hydronium ion. So, and this doesn't happen all the time. It happens, rarely does it happen, but it does happen. So this self-ionization of water, that means one of the water is acting as an acid, as a base. And if you watch the video on acid and bases, you notice that according to Bronsted, the water that donates the proton is the acid. So this is the acid. The one that accepts the proton is the base. So this is the base. So now we want to write the equilibrium constant expression for this equation. And when it's written, it will be Kw equal to hydronium ion concentration times hydroxide ion concentration. This is true also. Hydronium is used interchangeably with hydrogen ion, so both of them are acceptable. And in writing this equilibrium constant expression, you notice that water is constant and is not included, so it's a constant. So at 25 degrees Celsius, this is the Kw. How do we get this number? Let's look at this pH scale. Okay, let's use this one. Water is pH 7, is neutral. Okay, when it's neutral, the hydroxide ion and hydronium ion concentrations are equal, and that's what we see here. They are equal. So from that Kw, if Kw is hydronium ion concentration times hydroxide ion concentration, that means when you multiply them, is 1.00 times 10 to negative 14. Also, we can also notice that even if you have, let's say, battery, okay, you see the hydroxide ion concentration here, hydronium ion concentration here, but both of them will also be equal. Okay, if you multiply them out, it will be equal to 1.00 times 10 to negative 14. Okay, so that's what is here. So this is what it is. That's how we get that. That's the multiply. When they're multiplied, you get that. Okay. Let's look at blood. Blood has this hydroxide ion concentration and hydronium ion concentration. So you find out that using the formula Kw, which is equal to hydronium ion concentration times hydroxide ion concentration, you find out that both will come out to 10 to 1.0 times 10 to negative 14. So it doesn't matter. The product of both of them will always come out to that. So this equation is true for all dilute aqueous solutions at 25 degrees Celsius. So the relative concentrations of hydronium and hydroxide ion concentrations are different in acidic and basic solutions. However, the product of the two concentrations must remain equal to 1.00 times 10 to negative 14. So we can look at that. If we have blood sample, like in that simulation, the hydroxide ion concentration is, hydronium ion concentration is 4.0 times 10 to that. This is molar. Most times it's kind of not written, but that's what this concentration means. And then hydroxide ion concentration is 2.5 times 10 to negative 7. So we find out that if we plug it into this, it will, and we multiply it out, that is 4.0 times 10 to negative 18. Times 2.5 times 10 to 17, it will come out to 1.0 times 10 to 14. Okay, so that's, most times this is, many books don't include it, but it's m squared, that's the unit. So that's good to know. Let's look at an example. The concentration of hydroxide ion in a solution at 25 degrees Celsius is 0.150 molar. Determine the concentration of hydronium ions in the solution. So this is the example. So we look at what we know. The concentration, we know hydroxyl. We write first what we know. We know this is 0.150 molar. Determine the concentration of, we do not know this. Okay. From what we've done so far, we know Kw is 1.00 times 10 to negative 14. So with this information, I think this is pretty straightforward. We have, let me draw this line here so it's cleaner. Kw is this concentration. Then we have this. Okay, we do not know hydronium ion concentration, so we have to isolate that. So that will be this divided by so we know this, and we know 0.150. This should be this, then this cross out that. And then This will be 6.67 times 10 to negative 14 molar. So that will be 6.67. Hydronium ion concentration is 6.67 times 10 to negative 14 molar. So that's how to, using that relationship, we are able to calculate that. This is not always written, it's always written without units, but it should be m squared. Okay. Pause this video and try this practice question. Pause the video and try this practice question. So the question is, the hydronium ion concentration in a solution is 3.16 times 10 to negative 3 molar. What is the hydroxide ion concentration? Always start to figure out what you know and what you do not know. You want to understand the question. So we know the hydronium ion concentration. That's 3.16 times 10 to this molar. Then what is the hydroxide ion concentration? That's it. That's only one equation, relationship we can use for this question. We know this, so we know Kw is 1.0 times 10 to 14. So we want to solve for hydroxide concentration. If that is the case, we isolate that by dividing both sides by this. So this will cross out. We can choose to put this on the left. It doesn't matter actually. Then this will be Kw over this. So we know Kw is 1.00 times 10 to negative 14. That should be m squared. Divide by 3.16 times 10 to this molar. So this will come out to, let's see, 3.16 times 10 to this molar. Hopefully you did it correctly. Let's look at pH scale. pH scale is qualitatively tells us about pH, how acidic or basic something is. You see different colors, like from 0 to 14. The scale goes from 0 to 14. Where 7 is neutral, like water. We looked at it. Water is neutral, is pH 7. And then anything below 7 is acidic, above 7 is basic or alkaline. Okay? So the greater the number of hydroxide ion present, the larger the value of pH. As number of hydrogen ion and hydronium ion increases, the pH value will decrease. Okay? So looking at this again, you see, pH value is less here. Okay? Then pH scale is a logarithmic scale. When you compare two substances such as lemon juice with pH 2, which I'll show you, and vinegar with pH 3, the lemon juice is actually 10 times more acidic than vinegar. This is because each unit on the pH scale represents a 10-fold increase in hydrogen ion concentration as you move towards 0. So let's look at this. So you'll see exactly what is going on. So this is the pH scale. But then if you want to see everything, so you see this, water is 7. Okay, water is 7, pH 7. Then at this, the hydronium ion concentration and hydroxide ion concentration are equal. What if we take battery acid? Is pH 1, which is consistent with that scale we looked at, 1.00. So now you see the hydronium ion concentration is higher, while the hydroxide ion concentration is less. So the more the hydronium ion concentration is, the less the pH, which is acidic. What if we look at hand soap? Look at it. Hand soap pH 10. Look at it, hydronium ion concentration is more, while hydroxide ion concentration is less, leading to higher pH. Okay, so this explains how we can relate the pH to the concentration of hydroxide or hydronium ion concentration. So let's look at the pH calculation. To calculate pH, the negative log of the concentration of hydrogen ion or hydronium ion is calculated. Hydronium ion and hydrogen ion are used interchangeably, so you can use either of them. They mean the same thing. So let's look at an example. What is the pH of 0.050 molar nitric acid? We looked at the naming of hydric acids in acid-base video. Okay, so here, this question, you have to understand it. It's just pH of 0.050 molar nitric acid. Okay, so because nitric acid is 100% ionized, the concentration of hydronium ion in solution will be equal to the original concentration of nitric acid. So each nitric acid molecule that was originally present ionizes into one hydrogen ion or hydronium ion and one nitrate ion. So let's look at this example together. So this is an example. What is the pH of 0.050 molar NHO3? So what do we know? What do we not know? What is pH? We do not know pH. Remember, this is equal to hydronium ion concentration. So that's equal to 0.050 molar. So that's the only thing we know. But we looked at this formula. Okay, do we have all we need? Yes, we do. So you have to have scientific calculator. So this is 0.050 mole. That's it. You plug this in using your scientific calculator. Each calculator is different, so you just have to understand your manual. This will be pH will be equal to 1.3. 1.3. Yeah. So this is the pH of this, okay? This is the pH of 0.050 molar HNO3. Pause video and do this practice question. Pause the video and do this practice question. So hopefully you did it. Let's look at it together. Again, we analyze the problem. What is the pH? Okay, pH we do not know. That contains 0.35 molar of hydroxide, 0.35 molar of hydroxide ion. Okay, so pH, from what we know so far, I write it here. pH is negative log of hydronium ion concentration. Do we know hydronium ion concentration? No. We do not know that. So we have to figure that out. How can we find that? We can use this, which we already did before. Again, we want to find hydronium ion concentration. We know hydroxide, so we divide by hydroxide ion concentration. So now, remember, it doesn't matter if this is on the right or left, it doesn't matter. So this we already know, this information, Kw over 0.35 molar. Remember, this is supposed to be this. So with that, it will be 2.9 times 10 to 14 molar hydronium. Now, pH will be negative log of 2.9 times 10 to negative 14 molar, which will give 13.54 pH. So pH 13.54. So you have to apply what we learned before in this particular question. So let's look at the pOH concept. The concentration of the hydroxide ion can be expressed logarithmically by the pOH. pOH of a solution is the negative logarithm of the hydroxide ion concentration. So this is very similar to pH. So the pOH equals a negative log of hydroxide ion concentration. Okay, so very similar to pH. Remember, pH is a negative log of hydronium ion concentration. So the pH of the solution is related to the pOH as shown below. pH plus pOH equals to 14.00. Okay. So now let's look at this example. It said find the hydroxide ion concentration of a solution with a pH of 4.42. Find the hydroxide ion concentration of a solution with a pH 4.42. So again, we have to understand the question. Find the hydroxide ion concentration. This is hydroxide. We do not know that of a solution with pH. We know the pH 4.42. We want to find the hydroxide ion concentration, but we know the pH. So in this type of question, we have to use a different relationship that we haven't used before. Though we know pOH plus pH equal to 14.00, can we use this? No, because there's no concentration, so that cannot be used. But there's another relationship, which is 10 to negative pOH. Okay, so this is anti-log. We have to go anti-log in our calculator to figure this out. So if we do that, it will be 2.6 times 10 to, that's it. Find the hydroxide ion. This is hydroxide ion concentration. So this is very easy, just like we use a different formula. A different formula is introduced, which is using just anti-log of the other one. So because we know pOH is water negative, log is not this one. And then we also, just to remind you, we know that pOH, it was a negative log of that. Okay. So we know the pOH, we don't know this, we use the anti-log. So this is expressed in this form to get that. Also, when the pH of a solution is known, the concentration of the hydrogen ion or hydronium ion can be calculated. So the inverse of the logarithm is, the anti-log is this. So that's how we, remember the other one we put hydroxide, then we have pOH here. So we can do that for if we want hydronium ion concentration, is the inverse of logarithm also is used. Okay, so this is so relationship. This if I recommend this for somebody who is struggling. This may help, but if you are not struggling, I don't think you need it. Okay, it depends on where you are. This is like summary of everything. So, but you can have it handy before you do the more practice questions, which is this. So pause the video and do these practice questions. Pause the video and do these practice questions. So let's look at this practice question. What is the pOH of So we don't know the pOH. Again, this is hydrochloric acid, and the strong acid is 100% dissociated. Because of that, the hydronium ion concentration will be equal to hydrogen ion concentration. So that will be 0.0235 molar. Okay, now how do we do this? Remember, as I said, because hydrochloric acid is 100% ionized, the concentration of hydronium ion solution will be equal to the original concentration of hydrochloric acid. Okay, so if we know we want to solve pOH, so we should know, to solve pOH, we should know the concentration of hydroxide ion. Since we do not know that, to figure out this out, we have to use Kw equal to this. Okay, which is, we divide both sides by hydronium ion concentration. Okay, now if you want, you can bring this to the left, it doesn't matter. So this will be 1.00 times 10 to negative 14. The unit is supposed to be this, all over 0.0235 molar. That's what this is equal to. This cross out this. So this will come out to be 4.26 times 10 to negative 13 molar of hydroxide ion. We are not done. We're supposed to calculate pOH. So, and we know that pOH is equal to negative log of hydroxide ion concentration. So, which will be negative log of 4.26 times 10 to negative 13 molar, which will be, you plug it in your calculator, you get pOH is that. Hopefully you got it correct. So for, yeah. So I hope you solve for this, B and C. If you did, this is the answer to that. Okay. That's it for today. Thank you.